From microscopes to eyeglasses, optical devices shape how we see the world and even understand the universe. In this video, we'll explore how mirrors and lenses form images and dive into the physics behind the human eye. We'll also break down how vision correction works, turning blurry sights into sharp clarity with a little help from physics. Our understanding of optical devices will require us to know about our previous unit on optics. That includes reflection, with the law of reflection stating that the angle of incidence will be equal to the angle reflected for a light ray encountering a reflective surface, and refraction, which means that light rays will obey Snell's law or the law of refraction when passing from one medium to another. Ultimately, by tracing out these light rays, our eyes are able to see objects at a far distance away. So we'll need to think about light rays, which is an idealized straight line path that a light wave will follow, and we'll think about essentially like a laser beam and where a straight light ray would travel either when it hits a reflective surface or when it passes from one medium to another. And basically the way that we see objects is by forming images, and image formation essentially happens by this process. Light rays will come from a light source and strike some object, and then that object will emit those light rays in every direction out of the object. And so some of these light rays bouncing off the object could be redirected as they bounce off of a reflective surface to our eye. That would be like by reflection from a mirror. Or some of these light rays could also be bent by refraction using a lens of some kind, and we could use that to allow for light rays to meet our eye. In this way, we can ultimately perceive objects in a far distance by picking up the light rays that are bouncing off of that object. And so we essentially form an image on our eye of an object that we're looking at in the distance. This is called image formation. And we can form two types of images. A real image is formed when light rays actually converge to a single point, and this real image could be projected onto a screen. So we might get a real image when we're looking at an object in a mirror, and we see that the light rays bounce off that mirror and converge on a single point. Or we might get a real image when we're using a camera to impress upon an image onto a film in that camera. Or we might use a magnifying glass to project a real image. So this is what we mean by saying we can project a real image. We have an object, this candle, sending out light rays in every direction. Some of those light rays get picked up by this lens and bent toward this single point so that you can see that on a screen or a wall behind that lens, we can actually form a real image that can be projected. We contrast this with a virtual image, which is formed when light rays diverge from one single point and do not converge onto a single point. And these virtual images cannot be projected onto a screen. If we were to try to project this onto a wall or screen, it would just appear as a diffuse, blurry object. And we can get a virtual image in the case of a plane mirror, where we see light rays bouncing off of this bottle right here, off of this object, and when they hit this mirror, they seem to diverge. And what we can say is that a virtual image forms behind the mirror as if that's where the light is actually coming from that virtual image. In this way, we can see that this candle that's sending out light in every direction, when we send it through the lens, it doesn't actually project anything behind that lens, but we can see an image formed within the lens itself. This is a virtual image. A plane mirror is a flat reflective surface that forms a virtual image because light rays diverge when they come from the object and hit that mirror. This is the same kind of mirror that you're used to using in your daily life. And so what we would notice is that if we trace light rays coming from the top of this bottle, we can sort of imagine two very similar light rays, one a little bit lower than the other. They're just barely offset. And we will notice that when these light rays hit the mirror, that they diverge. They do not actually converge to a single point after that mirror. And so this implies that we will have a virtual image because the light rays are diverging. Now, a virtual image is kind of hard to perceive and understand what it means, but essentially it means that because these light rays here coming from the object that bounce off the mirror are diverging, that it sort of seems like there is an object behind the mirror. You've seen this when you look in the mirror. It looks like there's an object behind the mirror, but you know there is not actually an object behind the mirror. If we were to put a projection screen behind the mirror, it's not like we would see a projected image of that object. Instead, this virtual image acts as if it is the source of light if we had no mirror there at all. If we had no mirror there at all and we didn't think about this object and instead just thought about the virtual image, it does appear as if light rays are coming directly from that virtual image, traveling through the mirror that we imagine not being there. And so this virtual image simulates what an object would look like if it was placed at that location. And for a plane mirror, the object distance will end up being equal to the image distance. There will be no magnification. This will be an exact replica of what is seen on the other side of the mirror. And we would say that the distance of the object is equal to the distance of the image in that situation. We can contrast a plain flat mirror with a spherical mirror, which is essentially a curved mirror that causes light rays to bend toward a central point when they encounter that reflective surface. And we can have two types of spherical mirrors. We can have a concave mirror and a convex mirror. A concave mirror is a spherical mirror that curves inward, causing for all parallel light rays that hit that mirror to be reflected through a focal point. This focal point we label as F. And we can calculate that focal point as being 1/2 the radius of curvature for this spherical mirror. So this spherical mirror is basically a circle, right? And the center of that circle we would call the center of curvature, and it has a specific radius of curvature associated with that center of curvature, and the focal point is halfway between the center of curvature and the reflective surface of the mirror. On the other hand, a convex mirror is a mirror that is curved outwards so that parallel light rays encountering that reflective surface will diverge. They will be sent outward in every direction if parallel light rays hit this reflective surface. And we would say that this is called a diverging mirror, whereas the concave mirror was considered a converging mirror, because in concave, all the light rays will converge to a central point, whereas in convex, all the light rays that come in parallel will diverge from a central point. And that central point that the light rays appear to be diverging from would also be called the focal point F of this mirror. And you can still solve for that focal point the same way that we did for the concave mirror. But the difference is that with a convex mirror, we will see that the focal point is behind the reflective surface, and we mark the center of curvature behind the reflective surface. So we sort of need to think about if these parallel light rays were coming in, they would be directed off of that reflecting surface such that they could be traced backward through the focal point. In order to better understand how we form images with mirrors and lenses, we need to use ray tracing, which is a technique that tracks the individual light rays coming from one point on an object. We know that this object has light going out in every direction, so essentially we're only going to track the light rays. We're only going to do ray tracing from the top of the object, and we're just going to assume that all of the other light rays coming from like the middle of the object or the bottom of the object will behave in the same way. So let's go ahead and try to draw out some light rays for this object. To do ray tracing, first you need to draw the P ray, which is a light ray that comes in parallel toward the mirror and is reflected through the focal point. This first blue ray is called the P ray, and we will notice that after the parallel light ray reflects, it becomes what we would call an F ray. An F ray is a light ray directed from the object through the focal point, and when it reflects off of that surface, it will be reflected parallel. So in this way, the P ray and the F ray are like inverses of each other. The F ray goes through the focal point and when reflected essentially becomes a P ray outgoing from that mirror. We can also draw some other critical rays like the C ray, which passes through the center of curvature. And we will notice that for a light ray passing from this object to the center of curvature, that it will encounter the reflective surface at a 90-degree angle such that it is reflected back exactly the way that it came. We can also draw the V ray, which is the vertex ray. This is drawn toward the vertex point of the mirror. That's the center of the mirror, bisected by what we would call the principal axis that our object rests on, or perhaps we could also sometimes call that the optical axis. And the V ray will come from the top of the object, go toward the vertex of the mirror, and it will be reflected with an angle that is equal to the incident angle, obeying the law of reflection. And we now notice that when we trace where all these rays go, they all seem to meet up at one point. And at that point, that is where our image would form. The top of the object has light rays going out and hitting this mirror and reconverging back at this point. And so that would be where the top of the image appears to be. And our object here is just this red arrow. And it looks like our image in this case of ray tracing is upside down. It is smaller than the original object. And it appears to be a real image because all the light rays are converging. On the other hand, though, we could have more complex ray tracing. So if we look at for a convex mirror down here, we would have our P ray coming in parallel, and it would reflect in a way that is directed through the focal point. But for a convex mirror, remember, the focal point is behind the mirror. No light actually makes it behind a mirror. It all is all reflected. So that P ray needs to be reflected off of the reflective surface such that it is directed through the focal point. And we could do that same type of analysis with the other light rays for this convex mirror. If we draw the F ray, our red line needs to be directed toward the focal point beyond the mirror. But then when the light ray actually reflects, it comes off of that reflective surface parallel. That'd be the F ray for this convex mirror. We have the C ray, which is the purple one, directed toward the center of curvature, and it just reflects back exactly the way that it came. And then we have the V ray, which is the green arrow. It comes from the top of the object toward the vertex of the mirror and is reflected with an angle that is equal to its incident angle, according to the law of reflection. In this way, with convex mirrors, we saw that the real light rays, the solid lines, diverge when they hit this reflective surface. All of these light rays are going every which direction, and they will never actually converge to form a real image. In this case, what we did was we traced back virtual light rays. We imagined what light would look like if there was light coming from the other side of the mirror, and what an object would look like if there was light coming from the other side of the mirror would be like what this virtual image shows. So again, we used virtual light rays to trace the reflected rays backward in this case, because they did not converge. And when we trace our virtual light rays backward, we do see that those dashed lines do converge to one point, forming an image at that point where the light rays cross, and this would be a virtual image. While ray tracing can be used to geometrically predict where images will form, we actually can also use equations, and the first one will be called the spherical mirror equation, which essentially takes the object distance DO in meters, the image distance DI in meters, and the focal length, which is the distance from the mirror to the focal point, and it relates them all in the spherical mirror equation, where 1 over F equals 1 over DO plus 1 over DI. All of the units are given, and sometimes DO will be written as the letter P, and sometimes it will be written as Q, but I prefer using the DO and DI. We can calculate a magnification based on these results. The magnification of a mirror will essentially cause for an image to appear larger or smaller than the actual object, and we can calculate the magnification as being the ratio of the image height versus the object height. Both would be measured in meters, and in this way we can also relate the magnification to the image distance over the object distance, with a negative sign being in there. It's important to keep in mind that there are sign conventions for spherical mirrors. So if we have a positive focal length, that would mean that we have a concave mirror versus a negative focal length, which would be a convex mirror. If our object distance will usually be labeled positive, and that essentially means that it's in front of the mirror. We usually want to draw that on the left side of these diagrams. But if our object is negative in distance, that would imply that we have a virtual object. Usually you won't have to deal with that so much. If our image distance is a positive value, then that means that we form a real image. But if our image distance comes out to be a negative value in this equation, then we know that that is a virtual image. And lastly, for our magnification, if we have a positive magnification, that would mean that our image was upright compared to our object. And if we had a negative magnification, that would mean that our image is inverted compared to the object. And also we can have a magnification less than 1 or greater than 1, which will indicate if the image will be reduced in size or magnified in size comparing to the object respectively. So spherical mirrors will reflect light rays in order to form a real or virtual image. But we can also use refraction from a spherical interface to form an image as well. And so we can calculate the object distance and the image distance of some kind of spherical interface based on the indices of refraction. We can calculate and predict where an object, where an image distance will be and where an object distance will be based on the indices of refraction of the medium where the object is placed and the medium where the image is placed. And if we take the difference of those indices with the radius of curvature in there as well in meters, then we can ultimately solve for a variable of interest in this equation. We use the letter hook P. This is a hook P. Since there's a lot of P's for pressures and powers, we want to try to do our best to make sure that we distinguish them differently. So I use hook P for the optical power or the refractive power of an interface. This hook PSI is specifically the refractive power for a spherical interface, and this power is actually measured in inverse meters is what you would get here, and we call that inverse meter unit a diopter, D. This is the literal number that is on an eyeglass's prescription, is the optical power. Now, I don't expect this equation to come up very much because it mostly is building toward our idea about lenses, but there are sign conventions for single refractive interfaces, and there is a magnification equation, but again, these both will not come up too much because this is building toward our idea about lenses. A thin lens is an optical device that can bend light rays due to refraction. This thin lens will also have a focal length and focal point, just like you saw with your curved mirrors. And a converging lens will cause for parallel light rays to come in toward that lens and then be bent by refraction such that they all pass through a focal point F on the other side of the lens. On the other hand, we could have a diverging lens, which has parallel light rays coming in, and when those hit the lens, they will be bent outward by refraction. Just by the shape of this diverging lens, we would see that parallel light rays would diverge outward and not ever reconverge somewhere. So sometimes we call a converging lens a convex lens based on its football-like shape. It's thicker in the middle and thinner on the edges. And we call a diverging lens a concave lens because it is thinner in the middle and thicker on the edges. Similar to spherical mirrors, we can also do ray tracing for thin lenses, which have two curved edges. For ray tracing with thin lenses, we still draw a P ray, which comes in parallel to the lens and then is bent such that it passes through the focal point F on the other side of the lens. We still have an F ray, the purple line, which goes through the focal point and is bent such that it emerges parallel from the lens. We have a C ray, which passes through the center of the lens this time, not the center of curvature, but the center of the lens. And this C ray ends up passing through the lens completely unbent. It will not experience a total refraction. And we can say again, the image will form where the light rays cross. So in this convex lens up here, we see that the P ray, C ray, and F ray are all bent such that they converge at one point on the other side of the lens. And that would mean that we form a real image from this convex lens as long as our object is outside of the focal point. We could think about, though, a concave lens, this middle one, where we have the P ray coming in and being bent outward. That P ray will be bent outward such that it could be traced backward through the focal point. And you will notice for these lenses, since they're symmetrical, there are two focal points, a near focal point on the close side and a far focal point on the far side. The P ray then for this concave lens would be the purple line. It's directed toward the far focal point, and it would be bent outward from that diverging lens such that it emerges parallel. And then, of course, the C ray for a lens goes straight through the lens. And you will notice that on the other end of this lens, that all of the light rays diverge. That's why we call it a diverging lens. These light rays will not meet up in reality. And so we're going to form a virtual image from this arrangement. And that means that we need to trace these refracted rays backward as dashed lines, dash, dash, dash. And we will see that when we trace the virtual light rays backward, they do converge, forming a virtual image at this location for this diverging lens. Now, with lenses, we could also have a unique situation where with a convex lens, we have our object placed in front of the focal point for that convex lens. So here's my object. It's a vertical arrow, a solid arrow, and I'm going to try to do some ray tracing for this. I will draw the P ray, which comes in parallel and is bent through the focal point. I'll draw the C ray, which goes through the center of the lens and passes through unbent. And I will draw the F ray, which is a little tricky for this one because the near focal point is behind the object in this case. So I need to draw the F ray such that it goes toward the lens as if it was coming from the focal point. It's directed through the focal point, off the top of the object and through the lens, such that when it hits that lens axis, it is bent and emerges parallel. Even if the lens isn't drawn that entire distance, we are assuming that these thin lenses are like infinitely long. And so really there's a lens axis that extends beyond that lens. And so this F ray can be drawn toward that lens axis and will be bent such that it emerges parallel. And you'll notice on the other side of this lens that all of these light rays diverge, even for a converging lens. And that's because our object distance is less than our focal length. It's a unique situation, a regime swap. And when we trace backward these divergent light rays, as if we needed to trace backwards some virtual light rays, the dashed lines do all converge on one point, and so we end up forming a virtual image in front of the lens for this convex lens with an object distance that is less than the focal length. So one more time, lenses are definitely a little bit tricky, but we have convex lens and concave lenses, and essentially we could think about if the object was placed behind the focal point or in front of the focal point. If it's placed behind the focal point, this is going to form a real image, and that would be inverted, and its size might depend on how close the object is to the focal point. And so what you might expect for that is something like this, where this lens leads to an inverted image within the lens that could be projected onto a screen. Now, the tricky part is when you have an object in front of the focal point for a convex lens. That's like this second case right here. And when we trace out all those light rays, we see we form a virtual image on the same side as the object. And so what that means is that image cannot be projected onto a screen. If I put a screen where that image should appear, it would not pick up an image on that projection screen. However, the light rays coming from that virtual image could be picked up by another lens and rebent to form a real image. So what a virtual image might look like is what this guy is doing here. He's got a very powerful magnifying glass and has his face in front of the focal point of that magnifying glass. And so what happens is we form an image within the magnifying glass itself that looks like the object did. You see the object here is smaller than the image. So what's going on here is the object, the person's face, ends up magnifying within that lens. It's upright. But if we were to put a screen behind this magnifying glass, we would not actually be able to project that light, the image of this person's eye. It's not a real image, it's a virtual image. Now with concave lenses, we still form virtual images. In fact, with concave lenses, we form a virtual image in either case, whether the object is in front of or behind the focal point. And so what that might look like is these lenses over here, where we take a large object and we shrink it down, maintaining its same orientation. And so you can see like this tree right here where we have a large tree in the distance that's blurry. We can use a diverging lens to form a virtual image within the lens that is shrunken at the same orientation, but perhaps more in focus. Now, thin lenses actually obey the same equation as the spherical mirror equation. The thin lens equation says that 1 over the focal length equals 1 over the distance of the object plus 1 over the distance of the image. And we have similar sign conventions for thin lenses. They're not quite the same, but they're similar. For our positive focal length, that would mean we have a converging lens, and a negative focal length means a diverging lens. A positive object distance implies that it's a real object, so that's usually what we're going to have, and we're not often going to have a negative object distance. But our image distance will be positive if we form a real image and negative if we form a virtual image. That's the same as mirrors. And our magnification will be positive for an upright image and negative for an inverted image. And our magnification would be less than 1 or greater than 1 if the object is reduced or magnified respectively in size. The magnification is calculated with the same equation as the spherical mirrors. So let's give this example a shot. We have a convex lens here with an object distance of 5 centimeters and a focal length of 4 centimeters. We're asked first to solve for the distance of the image, di, and what is the magnification, and then is the image virtual or real. So let's start our problems the same way we always start our problems. We label our knowns and unknowns. We have a DO of 5 centimeters and F of 4 centimeters, and you can choose to put these in the standard units if you want, but let's actually just leave them in the non-standard units for once. The distance of the image is our unknown, so let's go ahead and solve for that using the thin lens equation. 1 over F equals 1 over DO plus 1 over DI. And here we see from our thin lens equation that we get 20 centimeters for our distance of our image. We can now plug this into our magnification. Here we see that our magnification equals -4. The magnification is unitless. It's just a ratio of the distance of the image over the distance of the object. And so the negative implies that we have an inverted image and that it's going to be larger than our object, 4 times larger in the negative direction than our object. In this case, there are a couple of ways of determining that we have a real image. First off, we could just remember the regime. We have an object distance that is outside of the focal length for a convex lens, so this will form a real image. By the ray tracing, we see that the light rays all converge, and we can project this image onto a screen, so that implies that it's a real image. And also, our distance of our image is positive, so this would be a real image. Let's give another example a shot. Here we have an object that is 10 centimeters away from a concave lens, and our image distance is given to us as 4 centimeters. So it's sort of like the arrangement that we have here. We have a object distance, DO, that is 10 centimeters, but an image distance that is only 4 centimeters with a focal length that we do not know. We need to solve for the focal length. We need to solve for the magnification, and if the image is virtual or real. So we'll use the same steps as last time. But now there's something that we need to be careful about. Because our image is on the same side as our object, we don't want to forget our sign conventions. And if we have an image distance that's on the same side as our object, that's one indicator that the image distance actually needs to be negative. But also we know for a concave lens, everywhere that we place our object will yield a virtual image, and a virtual image will have image distance that is negative. So you got to watch out for the sign conventions for these lenses. Here we get a focal length for this lens of negative 6.67 centimeters. And remember, that negative implies that this is a concave lens. Concave lenses have negative focal lengths, and convex lenses have positive focal lengths. So far, everything is adding up. Let's check our magnification and if the image is real or not. Here we see that our magnification ends up being positive, implying that our image is upright compared to our object. This is our object. This is our image, and we see that the image is upright. It's the same orientation as our object, and it is also shrunken or reduced in size. That's because our magnification is less than 1. And in this case, we form a virtual image. There's a couple of ways that you could know that. First off, our focal length is negative, implying that this is a concave lens, and all concave lenses always form a virtual image. Also, we know that our distance of our image is a negative value, implying that it's a virtual image. And lastly, if we were to do the ray tracing, we would see that the refracted rays all diverge. Here we've drawn the P ray and the C ray. We have not drawn the F ray, which might look a little bit something like, let's say this, where it's directed toward a focal point at the far end and then emerges parallel. So we can use the thin lens equation to calculate the distance of an object or the distance of an image based on a lens's focal length. But that doesn't actually say anything about why lenses have different focal lengths. To determine the focal length of a lens, we use the lens maker's equation, which essentially relates the focal length of the lens to its geometry and the material that it's made of. Essentially, the index of refraction will dictate how much light rays bend when they encounter that lens, and the curvature of each end of the lens will essentially determine where the focal point is on the far side and the near side of a thin lens. In this way, we can calculate the refractive power or the optical power of a thin lens as hook P, which is just 1 over the focal length for a thin lens. And remember, the power is measured in diopters or inverse meters. The human eye is a complicated optical instrument that utilizes this idea of lenses to bend incoming light rays toward your retina so that you can form an image on the retina of your eye. Essentially, there are 2 main components that refract light rays. We have the cornea right here, which is like a spherical interface that we talked about a little bit. So we could determine the optical power of the cornea, assuming that it's a spherical interface. And then the iris, which is essentially the muscles around the pupil right here that contract or expand to allow for more light to enter the eye, will allow for the eye lens beyond the cornea to pick up light rays. And you can see that this eye lens is sort of like a thin lens with 2 curved edges. And so we can calculate the power of the eye lens using the lens maker's equation. And the total refractive power of our eye is the sum of the power of the cornea and the power of the lens. And ultimately, these 2 optical instruments, these 2 lenses, will bend incoming light rays like you see when you're looking at a tree in the distance. We look at the top or the bottom of the tree. The cornea and the lens bend the light rays such that they converge and form an image on your retina. Oddly enough, since this is a converging lens, the image that forms for a faraway object is inverted. And so really, the images that are being projected onto the retina of our eye are all upside down. But ever since a young age, our brains are capable of decoding that and flipping it neurologically so that we can see things right side up. Accommodation is the way that our eye changes its shape to focus on objects that are farther or closer away. In this way, we would say that the eye of a human has a far point. This is like the farthest distance away that we can see things clearly without any form of accommodation. No squinting, no changing of the size of our iris or anything like that. And we would say that normal standard vision has an infinite far point. Very far away objects we should be able to see clearly. We would also say that the eye has a near point. This is the closest object that you can view while still viewing it in focus. And essentially, normal vision has a near point of somewhere around 25 centimeters. And that basically means that the eye can clearly focus on objects that are 25 centimeters close to you, but any closer might be difficult for the eye to focus just based on the shape of the eye. Now, the fibers that actually cause for your eye to contract and expand get weaker as we age as humans. So the near point ends up suffering, and we end up having difficulty seeing near objects the older that we get, because the near point ends up increasing over time. Vision correction is what we do to correct for eye defects that cause for light rays to not be bent properly and meet on the retina. Myopia describes nearsightedness, which essentially means that all the light rays that are coming in toward your eye are focusing before your retina. They're being focused before the retina, so by the time that they actually reach your retina, they diverge a little bit, and an image would appear fuzzy if it was too far away. So we think about very far light rays being bent by your eye and ultimately converging in front of your retina. We contrast that with hyperopia, which is farsightedness, which essentially means that parallel light rays coming in toward your eye are not bent enough and that they converge behind your retina. So ultimately, the light rays that meet at your retina where you pick up the image are going to appear a little bit blurry if you're farsighted and you're looking at a near object. In this way, we can use a corrective lens to fix these issues that we might have. And we do that by administering either eyeglasses or contact lenses with a specific eye prescription. And the eye prescription that you have for your corrective lenses is a literal measurement of the optical power of the corrective lens placed in front of your eye. So if we need a stronger prescription, a stronger power, then we would need a focal length to correspond to that. Specifically, myopia means that light rays will focus in front of the eye, and in order to correct for this, we're essentially going to need to use a lens that bends the light rays outward a little bit as they enter your eye. So the main idea for myopia is that you can focus on objects that are close very clearly. The near point for people with myopia is essentially 25 centimeters, the standard value. But far objects do not focus very well because the far point shortens. Our far point that our eyes can make out ends up becoming less than infinity, shorter and shorter. And so we would need for some type of diverging lens to be used in order to correct for this. Myopia is corrected for using a concave lens or a diverging lens. Essentially, the light rays are bent too much if you didn't have a corrective lens in there. So we add in a diverging lens in front of your eye that takes parallel light rays that would otherwise go through and be bent so much that they focus in front of your retina. A diverging lens will bend those light rays outward a little bit, causing them to focus a little bit later in the point of the eye such that they focus correctly on the retina. So let's try an example for nearsighted folks. Your prescription for a nearsighted person reads negative 1.5 diopters. That's the power of the lens, so we could use that to calculate the focal length of this lens. And it says, what is the farthest distance that you can see without your glasses before it appears blurry? So since we have this corrective lens that can correct for myopia, then we can use this to assume something about how the eye is able to focus on objects. So let's go ahead and calculate our refractive power first. So that would be hook P is equal to 1 over F. And so if our hook P value is negative 1.5 meters to the minus 1, that's diopters, is equal to the inverse of the focal length, and we should be able to calculate our focal length. Here for my focal length, I get a value of negative 0.667 meters. So let's plug that into our thin lens equation. Now we have our focal length, but we don't have an object distance or image distance, at least not in the way that the question is written. So we need to think about that far point idea. What is the farthest distance that we can see without our glasses before it appears blurry? That means that we need to think about the far point. And for normal vision, the far point is equal to infinity. Of course, that far point is lesser for people with myopia, but we're going to assume that these corrective lenses correct for our eyes such that it would bring the vision to standard vision. So essentially, our far point describes an object distance of infinity. And so we can plug infinity in for our object distance. Now, that's a little bit tricky to plug in, but let's just think about this fraction. If we plug in our value for F, and if we plug in infinity for DO, then we should be able to solve this for DI because 1 over infinity essentially goes to 0. And so now we can go through and calculate what our image distance would be for this. What is the farthest distance that you can see? That essentially means what image would you be able to pick up by the help of this corrective lens? And so we end up getting an image distance that is also just the same as the focal length of our lens. Hyperopia describes farsightedness, and essentially this means that light rays coming in parallel toward your eye will end up focusing behind the retina. And that's why things appear a little bit blurry, because the light rays have not focused quite enough by the time they actually reach the back of your eye, which is where we pick up these images. With hyperopia, far objects can focus just fine. Our far point ends up still being the standard value of about infinity. But objects that are closer than the near point appear blurry, and for farsighted folks, the near point will be greater than the standard value of 25 centimeters. In this way, we basically need to use a corrective lens that will cause for light rays to bend a little bit more before they enter the eye. In other words, we need to use a convex lens or a converging lens in front of the eye to help these light rays bend so that they focus properly on the retina. All right, so let's try an example for a farsighted individual. Here they have a near point of 1.25 meters, and they want to be able to clearly see an object that is 25 centimeters away. What is the refractive power of a corrective lens that would be able to accomplish this? So again, we will use our thin lens equation. 1 over f equals 1 over do plus 1 over di, and we need to know what each of these values actually corresponds to. Here, our object distance is definitely 25 centimeters. They label that as the object. And then it says it wants a near point of 1.25 meters. That's essentially saying what our image distance should be if we apply this lens. So our image distance here is 1.25 meters. I can already see that these two are in different units, so we're going to want to make sure we choose a unit to use for this. Let's go ahead and put everything into meters, so I'll make sure that that object distance is in meters, and now we can plug this into the thin lens equation to figure out our focal length and our power. One small thing to note, though, is that we have a converging lens here, and we're going to assume that our object is very close, right? Because we're talking about a farsighted individual trying to see things that are close. So this image is actually going to form a virtual image. We're talking about an object that is in front of the focal length of our lens. So actually, this image distance should also be negative because this is a virtual image. So you're going to have to ask yourself if you think that the image would be a virtual image or a real image, and make sure you assign the proper sign convention for that. And so in this example, we get 3.2 for our refractive power for our lens, and we could solve for a focal length if we needed to, but those are just inverses of each other. So we've solved for the power of this lens that would allow us to focus on an object that is very close. Let's just go ahead and double check that that object is indeed in front of the focal length. The focal length is 0.3125 meters, or about 31 centimeters, and that means that our object is in front of the focal length, and that means that we will get a virtual image for this converging lens. Now, there actually is one more form of diffraction that we haven't spoken about yet, and that's called circular aperture diffraction. We've spoken about double slit diffraction, single slit diffraction, grating diffraction, but also if we send light through just a small circular pinhole, we will even have light experiencing an interference pattern and diffraction through that small pinhole. We say that the hole has a diameter of capital D. This aperture is like a circular opening that light can pass through, and we can calculate the diffraction pattern or interference pattern using a diffraction equation, which looks slightly different than what we've seen before. But for the first dark fringe, that will appear when we satisfy this equation shown here. And essentially what this means is that two objects that are very close to each other will have a bright central maximum in the middle of their interference pattern and then a dark spot. And as long as the central maximum of one object does not merge with the dark spot of the next object near it, we should be able to distinguish those two objects. This is like if you've ever seen two headlights coming at you from a distance. How far away do you actually need to be from that car before those two headlights appear to be one headlight? The way that we calculate that is by understanding circular aperture diffraction. And ultimately, the diffraction pattern is based on the diameter of the aperture, the size of our opening. So as we scale up the diameter of our opening, we notice that the interference pattern tightens. The Rayleigh criterion defines the diffraction limit, essentially what the angular spread is required to be able to distinguish two different objects. So if we have two different light sources, S1 and S2, separated by a distance x or delta x, based on their projection length L, we can determine how far apart those objects would need to be for us to be able to distinguish them as two separate objects. And so whenever this Rayleigh criterion is satisfied, we will be able to distinguish those two objects. As long as the diffraction angle, the sign of the diffraction angle, is greater than this number, then we will be able to distinguish these two objects and resolve them. Essentially, the Rayleigh criterion states that the central maximum of one light source must be beyond the first minimum of the other light source. Otherwise, those two light sources would appear to merge together and we wouldn't be able to distinguish them. And so just based on the trigonometry of the situation, we know that the sine of that diffraction angle theta would be a ratio between the opposite leg and the hypotenuse. And so essentially we end up substituting x over L in for the sine of theta in this expression. So here's an example dealing with the Rayleigh criterion and vision correction. We are looking at a computer screen, much like the screen that you're looking at now. And it is about 25 centimeters away from our face. That's the near point. That's how close we can make out different objects as being distinguishable. And so we're asked, how close do the pixels need to be in a computer space so that you cannot distinguish them anymore? We're going to assume a diameter of 4 millimeters for your pupil. That's the size of the opening through which this light is going to bend and be distinguishable. And the light has a wavelength of 520 nanometers just for one of these pixels. How close would they have to be before I can't actually distinguish them as separate pixels? So let's go ahead and write out the Rayleigh criterion and try to get some numbers in for here. So here's our unknowns and known values. We're going to go ahead and solve for x in this expression. So here we get a result of 3.965 times 10 to the negative 5 meters, or maybe something somewhere around 40 micrometers. That would be how far apart our pixels need to be before we can actually distinguish them. So we want them to be closer together than that number. And that means that we need somewhere around 600 pixels per inch in our computer screen. This Rayleigh criterion is essentially what allows us to distinguish separate objects when using a lens in a microscope. The lens in a microscope has a numerical aperture, NA, which is a unitless number that characterizes the ability for a lens to resolve different angles of light. And so with this aperture will open or close, allowing for different spreads of light to be accepted by this microscope. And that essentially allows us to distinguish between two different objects that are sending light out in every direction. We can calculate the numerical aperture by this expression right here, where the numerical aperture is equal to the index of refraction of the medium through which that light is traveling. Usually that'll be air for an optical microscope. And that index of refraction is multiplied by the sine of the acceptance angle. And the acceptance angle is essentially the half angle that we solved for from the Rayleigh criterion. And so if you want to set your numerical aperture to be able to distinguish two objects that are a distance delta x apart, you will need to satisfy this expression. So that'll cover everything related to optical devices, lenses, mirrors, and the Rayleigh criterion. Next, we're going to move away from optics, but these ideas of light will still stay true. So make sure you keep this in mind for the next unit. Thanks for making it to the end of the video. I'll see you in the next one.